So, good evening, all of you. Uh, I'm Vijay Rahane, a PhD student in the IIT Delhi and the University of Queensland. So, today I'm here to discuss regarding the uh, NPTEL course, which entitled Structure, Stereochemistry, and Reactivity of Organic Compounds and Intermediates, a problem-solving approach. This course is taught on the NPTEL by Professor Amit Basak. He's a professor from the IIT Kharagpur, and mostly this course is for undergraduate level. And for this course particularly, there are a few reference books. Professors recommended this book to study the more detail. First one is the Organic Chemistry by Dick Clayden, the well-known book for the organic chemistry. Second one is the uh, McMurray, the Organic Chemistry by McMurray. And there are two different books are also there, like Stereochemistry of Organic Compound by D. Nasipuri, and another one is the Paul Bruce. So the course is of eight weeks, and it consists of different aspects of the stereochemistry. In the first week, generally it deals with the stereochemistry of the small organic structures, and mainly the concept of the symmetry. In the second week, in the course, the conformation of the saturated fusing systems will be studied. Similarly, in the third week, the more advanced problem in terms of 3D structure, determination of the chiral compound, and problems on this topic will be covered in the third week. In the fourth week, the stereoelectronic control on the comparison and the reactivity of the organic molecule, and some cyclization, intramolecular cyclization reaction will be studied in the fourth week. In the fifth week, the mainly in this course we deal with the organic intermediate, like a different organic we know the with the progress of the reaction, uh, we can see the different intermediate, like carbon intermediate, nitrogen intermediate, cation, anion. This kind of intermediate will be studied in the fifth and the sixth week. And in the seventh week, mainly the asymmetric reaction on the carbonyl carbon. We know the carbonyl carbon, it yes, sp2 carbon, and it's a kind of stereogenic center. So after reaction on that carbon, we can generate a new stereo center. So this type of reaction will be studied in the week 7. And in the week 8, the similarly the more advanced reaction and the problems based on it will be studied. This is the just general layout I have shown here. With the course of reaction, we can see this in the upcoming weeks. And you probably you may found there are the videos still, already uploaded for the second week, with the videos on the confirmation of the saturated fusing compound. And there are 4 to 5 lectures. You must go to that video, which is uploaded by Professor Amit Patel. So in the first week, what uh, what are the topics are covered in the first week? In the first week, we have seen the introduction to the structure and the stereochemistry. Mainly, we know the stereochemistry. What is this stereo means? Stereo means the arrangement of the different group. Suppose this one is the center, and the three-dimensional arrangement of the different attaching group around some center or some point. Suppose we can see the methane molecule, which contain the carbon and the 4 hydrogen. This central carbon, which has the four hydrogen attached in the 4 different directions. like this. We can this this bold bond, which indicating the hydrogen attached to this carbon, is above to the plane of this carbon, and the dotted line indicates the hydrogen is the below, and the line, the bond shown by the straight line is is representing the bonds are in the plane. So if we see the plane, in this plane there are one carbon, one hydrogen, and the second one hydrogen. These three hydrogen are in the plane, and these hydrogen are above the plane. These hydrogen are below the plane. These are the uh, basic structure of the methane molecule, in which the four bonds are attached to the central carbon atom, and why these bonds, four hydrogen atoms are attached. I'll just rub this one. So, and why it is important in case of the organic molecule? Because the organic molecule mainly consists of the carbon, and we can see the long chain carbon like a small molecule like a propane. In this one, there are eight hydrogen atoms, and the three carbon atoms are there, and all other are the mainly the main core of this molecule are built by the carbon and the hydrogen. Since the carbon attached to this attached, its quaternary carbon atom, means the central carbon has the four bond which are lie in the space. Uh, this we can see with the some advanced software like Gaussian. Hope you are able to see my screen. I will show the simple example here. You can see my screen, right? So see, this one is the carbon atom. Let's consider this one is the carbon atom, and to this carbon atom, there are four different groups are attached in the three-dimensional space. You can clearly able to visualize the structure of this molecule. In this one, there are four different groups are attached around the carbon atom. So and there are many possibility in which this these four atoms are attached to this central carbon atom. Means if we interchange these two molecules like a red and green, the structure will be not exactly same. This is because the chirality in the molecule. So this is why the stereochemistry is more important in case of the organic molecule. And slowly we see in the first week we have covered the symmetry. The symmetry, different symmetry and symmetry operation, symmetry symbol, and introduction to this introduction of the symmetry and point group. There are four main symmetry elements. In which the first one is the axis of symmetry. Second one is the center of symmetry. Third one is the plane of symmetry. And fourth one is the alternating axis of symmetry. The axis of symmetry is denoted by Cn. The center of symmetry is notation for the center of symmetry is the I. For the plane of symmetry, notation is sigma. It may be sigma h or sigma v or sigma d. With the course progress, we will see what is difference between the sigma h, sigma v, and sigma d. And fourth one is the alternating axis of symmetry, which is denoted by the Sn. These are the four elements of the symmetry, right? And among these four elements of symmetry, uh, there are two different classes. Like this axis of symmetry, I will differentiate this one in the two different categories, in which the proper element of symmetry and improper element of symmetry. I'll just add one more slide. Yes, yes. Proper element of symmetry, and in this one there will be the only the Cn. Cn means the axis of symmetry, and another three are the improper element of symmetry. In which the first one is the plane, second one is the center of inversion, and third one is the Sn axis, that is improper axis of symmetry. We will see what is different between this, what is meant by axis of symmetry. So axis of symmetry, suppose we have a molecule or any object. Let's consider like this, and here here in a group or something is attached to this one. So if you rotate this molecule by 180 degree uh, to the center, which is passes to the center of this molecule, this center one, I will just label it with this red color. And if you rotate this by 180 degree, not 180, this one need to rotate by 90 degree to get this the structure which looks like unchanged. Means this A, suppose I will just, for sake of convenience, I will just label this as A dash, A double dash, A triple dash. So after rotation, what kind of structure we will get? We'll get the structure like this, in which this A dash is in the place of this A double dash, right? So it's A dash. Since we have rotated this A dash come here at the position of A double dash, so it is here A dash. The A double dash will go here, and A triple dash will be go in this place. So if you see, just forget about this dash that we are just labeled for our understanding. The structure looks unchanged by rotating molecule, right? By rotating molecule by 120 degree. So we'll get this molecule, the same molecule which looks unchanged to the previous one. So these are the axis of symmetry. Similarly, we can see different examples, like we can take a cube and rotate it by, let's take a cube. See, and we'll just pass the axis through this one. So we can get the exactly similar structure by rotating it by 90 degree or 180 degree, right? Because after rotating this by 90 degree in this direction, suppose we can get this point will become here, this at this position. So by rotating this molecule, we can get uh, the structure, different structure. We can visualize this one by using this 3D model. Here is the, yeah. Suppose this one is the molecule, right? And if we pass the axis like through this one, through this two molecule, this center, the central situated carbon atom, and this one. So let's say this brown one is the hydrogen, and the central gray color is the carbon one, carbon atom, and we pass axis which is passes through this hydrogen and the centrally situated carbon atom, uh, and rotate this molecule by 120 degree. So once we rotate this molecule by 120 degree, we'll get the, see, if we passes axis through this one, we say the central hydrogen atom. Just keep an eye on this one, right? Here is the hydrogen, here is the carbon, and we rotate it by 120 degree like this. So how it looks, this look remain unchanged like this. Second operation also we can do another 120 degree rotation, also molecule look like unchanged. Third operation also we can do again rotate by 120 degree, this molecule looks unchanged. So this is the axis of axis of symmetry. In short, the molecule or the structure should look unchanged after performing this operation. And this operation, what is the operation we are performing on this molecule is the axis of rotation, that which is denoted by the Cn. The second element of symmetry is the improper element of symmetry. In which we'll take just first example. We'll take the example of the, firstly we'll see the inversion I. In this one, we will take the example of molecule. See, this is the molecule in which these bonds are in the plane. Let's say these are below the plane, and here it is above the plane. Correct. And here there will be below the plane and above the plane. Suppose here hydrogen atom is attached. and here also hydrogen atom is attached. Here bromine, let's take here also a bromine, and here chlorine, here fluorine. You can see it has a center of inversion. How? The center of inversion, the point at which we'll get the same atom when we go to different opposite direction, like here. From the center, if we move in this direction, we'll come up, we'll get this hydrogen. And with the opposite direction, if we go, then here we can get the hydrogen, right? So this is called as center of inversion I, which is denoted by I. Similarly, here also we can see here in this direction if we go, we'll see the bromine, and with the opposite direction there is also a bromine atom attached. Similarly, this chlorine above the plane, uh, is above the plane, and here below the plane. Here we can see from the center there are two in these two direction of this chlorine. Exactly, if we go opposite direction, we will found the chlorine atom. So this is a example of the inversion center. Let's take another example in which we will identify whether it has the center of inversion or not. Suppose this one is the square, and to this square, just to get better visualization, I will draw like this one. And here there is one hydrogen atom attached. In opposite direction, there is also hydrogen. Right? How we can draw here? Here like this. See, does this molecule have the center of inversion? Yes, it has the center of inversion. Here it is. So here is the center of inversion. If you go to this direction, we'll get here hydrogen. And exactly if you move exactly opposite direction, we can found hydrogen placed here. Right. So this molecule also having the center of inversion. But if you substitute this molecule with the chlorine atom, let's say the chlorine is in the downward direction. Here is the chlorine, and here also it is a down direction. So how it looks in this molecule? Here is the chlorine. Here also is the chlorine. Yes, here is chlorine. So these chlorine are in the same direction. So if we move toward this direction, and we are not able to found here chlorine to, so now in this molecule there is no center of inversion, right? Now it doesn't have any center of inversion because this chlorine, both the chlorine atom are in the same direction. So these are the some two examples of this center of inversion. Or uh, another one, another improper element of symmetry is the uh, plane of symmetry. In the plane of symmetry, well, let's take example of water molecule. Uh, Here hydrogen, central situated hydrogen atom, and to this hydrogen atom, one oxygen atom, central situated oxygen atom. To this oxygen atom, there is hydrogen. Another direction, there is alpha hydrogen, and these are the lone pair that no need to take into the consideration. Or no, right? To this water molecule, if you pass a plane which is perpendicular to this plane of this, let's say this slide. So how will be the plane? The plane will be like this, right? So see, if you place a mirror in which is crosses passing through this centrally situated oxygen atom, right? In this plane, you can see this direction. There is one hydrogen, and it's to the opposite also there is one hydrogen. So it has a plane of symmetry. This we can also look uh, with the 3D model, let's say this example. Another, it's not the water molecule. Let's let's see this example. In this one, if we let's see the molecule all way, right? In this molecule, this one is the carbon atom, and two, another three are hydrogen, which is attached to this carbon atom. And here is the oxygen and the hydrogen. This example of the methanol. So in this one, you can see, let's see like this, right? So the plane which is passes through these four atoms, like oxygen, this oxygen, red oxygen, this hydrogen, carbon, and this hydrogen. This the plane which is passes through these four atoms, which is the plane. You can see, and after we can divide this molecule in exactly two equal parts, right? By using this plane of symmetry operation. Let me draw here methane, right? As we have seen there, there is one carbon and oxygen, here hydrogen, and to this one there is hydrogen. One hydrogen is below the plane, second hydrogen is the above the plane. So the plane which is passes through this hydrogen, carbon, oxygen, and this hydrogen. That plane divide this methanol molecule into the two equal parts, and which are indistinguishable from each other. So this is the plane of symmetry, and this is improper element of symmetry, similar like the inversion. And still one element of symmetry is there, which is falling into the category of improper element of symmetry. That is ASEAN. ASEAN means improper alternating axis of symmetry. Let me just check the recording. Yeah, it's recording going on. Alternating axis of symmetry. This alternating axis is the combination of two different element of symmetry. This Sn, which is equals to the Cn plus sigma perpendicular. Uh, what what it means? It means if we let's take a let's we can with the help of example, uh, take a simple example. This one, suppose here is the hydrogen. Draw the perfectly. We need to do the reflection to this molecule. Uh, Instead of taking this difficult example, we'll take some simple example. Simple example first. Can take the example of a link system. I'll just insert one slide. we'll take example of Alin. Alin, how Alin, in this one, the hydrogen atom are attached like this to the sp2 carbon, and yeah, this is the Alin system. This is the, and we are taking example of the SN axis, that is alternating axis of symmetry, right? So in this one, uh, SN means Cn plus perpendicular sigma, sigma perpendicular, right? Uh, so we need to visualize how this possible, how it is possible to uh, get the identical structure, which is exactly similar to the previous one by doing these two operations like Cn and sigma perpendicular, right? Means we need to do the first Cn operation. Cn En is equal to 1, 2, 3, 4, like this. It's like a number, right? So this n represents here, and plus we need to do the sigma perpendicular. Let's check by this direction. Initially, you may find some difficulty to visualize this one. So still 1 to 2 weeks, you need to do the practice with the progress of this course. You can habitate with the get habit with the solve this question. So let's try the C4 axis here on this molecule. C4 axis. In this C4, once you do the C4 axis, so how this structure will look like through this axis we need to perform this operation. So once we do the C4 axis, this hydrogen atom which is in the plane, it come above the plane, right? And this hydrogen is in the plane, so it will go downside, and this carbon and all these things remain in the plane. And what happens to this one? Since it's above the plane, it go in the plane, right? It will do the rotation by the 90 degrees. Since we are performing C4 operation, so it will be in the plane. This hydrogen also will be below the plane. We need to pull it up, so it will by 90 degree, so it will be in the plane in this final structure. And then we need to take the reflection, which is perpendicular to the Cn. Since Cn we have did in this by this axis, so we need to do the reflection which is perpendicular to this plane, like this one. So plane which cuts the central carbon atom. So like this, we need to take a mirror plane to this. So once you place the mirror in this one here, so how this structure will look like the final structure one. In the final structure, the central carbon will be there only. So nothing will happen with this central carbon atom. So we'll drop first this central carbon atom, and here there will be double bond. Second side, up, this double bond comes here. This double bond comes go there. So let's label C1 and this one C double C dash C double dash. So this C double dash comes this side. So here will be just that C double dash, and this one will be here. Now see this hydrogen here above the plane. Once we reflect Here also it should be the above the plane, this hydrogen, and this another one below the plane. Similarly, here this hydrogen is, these two hydrogen are in the plane. Here after reflection, doesn't, it will not get affected. It just come to the opposite carbon, opposite direction. So we can see the previous structure, this structure, and this structure looks exactly similar, right? So what kind of operations we have did? We did the C4 plus sigma perpendicular, right? Therefore, this axis is labeled as the C4, sorry, S4 axis. This is the example of the alternating axis of symmetry, right? So with the course progress, we will see more advanced example. So you need to make practice. So these are the four basic elements of symmetry. Now we'll slowly move towards the, this is the example C. Here I have just pasted from the textbook. Here the same example we have as we seen here. Here this hydrogen, we did the C4 operation here. So this orange and the blue hydrogen, after the C4 you can see here, this once we did this one, we did the C4 operation, right? So here this C4 we can see, while C4, this is, they did in opposite direction. Sorry, here they have made this one. So it initially it is in the plane. So we did the C4 rotation to this direction, right? In this direction, this hydrogen is in the plane. Now we should do the C4 rotation, means the rotation by the 90 degree. 90 degree. So the in the plane, initially it is in the plane. Now it will go the, and this orange hydrogen is in the plane. It come above the plane, right? And here also similarly, since it is below the plane, we have to pull it up, right, by 90 degree. So how it will look like? This hydrogen will be go in the plane. Similarly, here is one hydrogen. We will label it by this one, right? So this hydrogen initially it's above the plane. So we did a rotation like this. Let's say anti-clockwise. So it above the, when initially it's above the plane, it will go in the plane, because since we are did by the 90 degree only, so it will go in the plane. And so this operation is the C4 operation. Now we need to take a reflection through the perpendicular mirror plane, which is mirror plane perpendicular to this C4 axis, right? So once you take this plane, let's pass this plane to this one, right? Once you pass a mirror plane to the axis perpendicular to this to this perpendicular axis, we'll get this blue hydrogen which go exactly opposite side, but being it is dotted, it will be remain there only, right? Here is this hydrogen. Since we have passes mirror plane, so this hydrogen go here, this blue hydrogen come here. Similarly, orange hydrogen go here, this red hydrogen come here, right? And now we can see, I will just clear all these things in between. So after all this operation, we can able to see this the structure, right? The structure A and the structure B, they are exactly looks same. Just forget about this colored, since we have labeled for our understanding. If they all the hydrogens, then these two structures are look like exactly same, which is the structure like a identical, right? So this symmetry operation means after performing these operations, like in we can say simple example like any kind of operation I, sigma, Cn, Sn. After performing this operation, the final molecule A should be look like the initial one. This A and the final. Suppose we start. Let's say this one A, and after performing this option, it's A dash. Just for labeling purpose, you see this A must be looks identical to the A dash, right? Then only this molecule contain this I or sigma or Cn or Sn. So these are the four elements of the symmetry, and there are some operations, symmetry operations. Like here I have enlisted. Like the first operation is the E. It is described as the identity operation, and its operator or the symbol for this one is the E, right? And its operation, like identity operation, means the after performing this operation, the molecule exactly the same. I mean, it's identical. We can say doing nothing with the molecule. It can be the identity operation. Let's take an example of C H H. Sorry, CH. Let's take here chlorine, here chlorine, here bromine. Let's take this example. And in this one, there will be uh, if we do this perform this operation, this molecule looks exactly the same. No need to do any operation, no need to take any what you can say Cn or Sn or I or sigma in this one. So after with this operator, after performing this E operation, the final one will be the identical one, remain unchanged. The second operation is the Cn operation, as we have seen here also. Here n-fold axis of symmetry, it is described as n-fold axis of symmetry, Cn, and its operator is the Cn. And here the Cn, the Cn, it will be the C1. C1 means the rotation by 360 degree or doing nothing with this molecule. Let's say Cn is equal to 1, 2, 3, 4, 5. So if you need to perform the C2 operation, so it's 360. So after performing this operation, like a Cn, the Cn C2 means we need to divide by 2. That is, it will be equal to the 80 degree. So we need to rotate molecule by this 360 by n. We need to perform operation C2 operation. If you have to perform C2 operation, then we need to divide by 360 by 2. Since we have written here 2, then it will be 360 by 2. Then it will be equal to 180 degree. If you need to perform operation C2, let's take an example of the C2 operation. I'll just insert one slide. Let's take an example of acetylene, and we need to perform the C2 operation. So how wire through this axis? So we need to rotate this molecule by 180 degree, 180 degree rotation. So here operation what these are the labeled hydrogen. So this hydrogen after 180 degree it will go this side. So here we have performed this C2 operation. Similarly, if we need to, if we have to perform the C3 operation, for the C3 operation, C3 which implies 360 degree divided by 3, it means 120. So we need to rotate a molecule by 120 degree. 120 degree. Let's say this if you perform this operation on this one. We need to perform the C3 operation. So we need to rotate this molecule by 120 degree. And so after performing this operation, how this molecule will look like? So here it will go here, it will go this one here. So C here, C, and here will A. So in this one we have performed the C3 operation, right? These are the example of the CN operation. Similarly, here is the sigma, means the plane of symmetry, right? Sigma describes the plane of symmetry, and this operator is called a sigma operator. So we need to take a reflection in the plane which leaves the molecule unchanged. We'll see with the help of example. Let's take the similar example. Right. Just we'll change it. After performing this operation, the molecule should remain unchanged. Let's here A, here B, and here also B suppose. So if we pass a plane which is passes through this central atom and this A, right? So this is the plane we have passed here, right? How it will be look like this A, sorry, this B and this B. Let's see labeled by this B, right? Just for understanding purpose, I have shown this B by two different colors. So after taking this reflection operation, how it will look like? The A will remain there only, right? The central atom also will be there only, but this blue B will go this side. Here will be the B, and this red B will be on the different direction. So what we have did here, we have did here the sigma operation. That is, we have taken the reflection plane. So the operator here is the sigma operator. Similarly, there is the I, which is correspond to the center of symmetry operation. In this center of symmetry operation, this operator is labeled as the small I, and in this one, the inversion through a center of symmetry leaves the molecule unchanged. After performing this operation, we need to take an inversion. As we have already seen the different element of symmetry. In this one, we have already seen the inversion center. In this one, what happens? We need to take an inversion through a center. Let's take a Simple example. Initially, we'll take a small example of this. Similarly, we'll take the example of the acetylene. So in this one, what you can see is these hydrogen are opposite to each other, and here there are two carbons. We can see here is the center of this molecule, and here we can see if you go opposite to this direction, there will be one hydrogen. Opposite to this direction, there will be also hydrogen. So it has the inversion center, right? So if you perform this inversion, the operation, right? This inversion, if you did this one, then what we will get? We will get this molecule, which is exactly similar to the previous one. But in this one, if this hydrogen is the labeled one, let's label it. Let's take this with the different color, orange hydrogen, right? This this after performing inversion operation, the orange hydrogen will go opposite direction after performing this inversion center of inversion. If you see some complicated example for this more some advanced example, we can take the example of this. Uh, let's have look here. This carbon to this there is the hydrogen which is in the plane. This hydrogen also in the plane, right? Let's now take hydrogen here. Take some other molecule like chlorine, chlorine, and here bromine, bromine. In this one, you can see here. See, here is the center. To the center, if we go to the one direction, we'll get here chlorine, and exactly opposite direction, we'll get here chlorine, another chlorine, right? So if we perform here inversion operation, so what structure we'll get? The structure which is exactly look the same. Just only thing is that this hydrogen will go here, right? This chlorine will this chlorine will go here, and this bromine will go to this opposite direction. Similarly, the carbon will also change its position after performing this inversion center operation. This example we can visualize by 3D model easily. So to visualize this, we'll take some example of this the molecule is which, to which the I is present, that is inversion center present. Yeah, here. So hope you are able to see this one. So what you can see here, see this is the molecule. Let's uh, consider this centrally situated hydrogen atom, and to this centrally situated this black colored hydrogen atom, there are three different groups are attached, like the red, green, and the blue. These three different groups are attached to one carbon. Similarly to the next carbon also, three different groups are attached, that the same exactly the same, right? So if you visualize this molecule in all possible direction, we can see there is one point, right, which has the which is the center of inversion point, right? Here it is, right? These two this point will just little zoom, right? Here, a point which is called the inversion center. Here we can see to this point. If we go opposite direction, we can see this opposite. If you able to visualize my arrow, right? You can see the arrow. This green one, which is exactly opposite to opposite, right? So this molecule have the inversion center. So if we perform the inversion operation, uh, how the molecule will look like? Let's take this molecule and take this all possible opposite direction, right? Here, right? So one previously this hydrogen, this green molecule was the position of this another green molecule, green atom. So this molecule, you can visualize it has the inversion center. Similarly, other atoms are also exactly in the opposite direction from this center of inversion. This point I am pointing here, right? So from this point, there are this red. When you go to the left direction, there will be the red, and if you go to the right, there will be a red. Similarly, if you check this blue, see these blue are exactly opposite to each other from this inversion center. Right. So this is the example of the inversion operation. And the last one, SN. In the SN, as we have previously seen in the case of the alternating axis of symmetry, n-fold improper rotation we need to perform. And this described the operator described as a SN. In this one, rotatory reflection operation consists of rotation through an angle that is 360 by n about to the axis, followed by the reflecting in a plane which is perpendicular to the axis. See here, insert one slide. Insert one slide. We need to perform a SN operation. So SN, what it means? SN means this we need to perform a CN plus sigma perpendicular, right? So N means the 1, 2, 3, obviously the number, and let's say that we need to take a S4 operation, right? So S4, the C4 we need to take, then we need to take the sigma perpendicular, then only these two operations we need to perform, right? Sigma perpendicular. First, we need to take the C4 and then sigma perpendicular. This we have seen in the case of this Alin system, right? Here we have performed this S4 operation. After performing this S4, the molecule remain unchanged. So these are some example of this different symmetry operations. Here you can see identity. If you one point we need to consider, if you rotate through an any axis by 360 degrees, that one is the identity operation. And after performing this, the molecule is exactly identical to the previous one. That is right. Here, n-fold rotation axis, that is CN axis. If we take the example of benzene, we can uh, rotate the molecule by C6. C6 means 360 degree divided by 6. What should the value it will come? That to this angle we need to rotate the molecule. So after performing this molecule, this will go interchanges with it will be in the adjacent position after performing this operation. Similarly, the inversion center, in the inversion center, as we have already seen there, after performing this one, see here one is exactly to these two are exactly opposite direction to each other. Right. N for improper rotation. If we N for improper rotation, it means let's take the example as shown here. We'll take this one. Yeah. See, this one is the example. Suppose this molecule attach here to a metal atom. Let's take a, suppose there will be a metal, and so it form a complex, and here it's entirely pi conjugated system, fully conjugated. Let's take the imaginary example just to understand. And in this one, there are three different groups are attached here. Like let's say a green group here attached, uh, here also attached, and here also. Right. These three green groups are exactly the same, and these are also attached here also. So if we need to perform a S6 operation, right? So we need to do the C6 and the sigma perpendicular to this S6. So let's take this S6, perform this S6 via axis which is passes to like this, right? So after performing this S6 operation, what we will get here. This metal will remain there only. Metal will remain there. Only the green group will change its position after performing this. So we need to perform this first C6 operation, right? C6. We need to rotate this molecule by, if we rotate the molecule, this group where it will come, this green group will come here, right? So here will be the second, this green group will be here, right? And the third green group will go here. Similarly, in the lower ring, this green group will be here. Second green group will be this green group, right here will go. It will go here, and this green group will go here, right? After this, we need to take a sigma perpendicular. That is, if we have passed this axis like this, right, vertically, we need to take a sigma which is perpendicular to this plane, to this axis, and not on this one. Here we need to take this sigma, right? After performing this sigma, how will the structure will look like? So here is the structure. Let's say fully forgotten. See, if we take a sigma perpendicular, this group, where it will go? It will go here, right? Exactly, entire this ring will shift upward, right? And upper ring will go downside. So we need to draw the ring. This ring, lower ring, and this upper ring should be identical, right? It should look like exactly same. And this lower ring we can draw here. Now you can compare this final structure, right? Sorry. This final structure look exact final structure exactly look like initial. So this is the improper rotation. N-fold improper rotation, that is SCL. And similarly, a mirror plane, as we have already seen a lot of example of this mirror plane. If the well, after taking a plane, this upper one will go downward, and lower one will go up. And there are sigma. You need to distinguish, as we have already seen. There is a sigma, but we need to differentiate how this sigma H, sigma V, and sigma D is there. So we know the mirror plane, which is denoted by the sigma. But what is sigma H? The sigma H is the plane which is perpendicular to the principal axis. Let's say here the example of benzene ring. In the benzene ring, I'll just add one slide. Let's take an example of the benzene. To the benzene, these all are the fully conjugated, right? And here the axis, let's take this axis, right? This axis passes to the center. It's the principal axis. Why it is principal axis? Highest, how many axes are possible to this benzene thing? As professor also discussed this thing in the video. In the benzene ring, in this one, how many different axes are possible? We can take C1. We can also take a C2. How the C2 can take? We can rotate molecule by 180 degrees. So this position will go here, right? So C2 also there, C3 also there. Like we can rotate this up to here. So 120-degree rotation, we can take, we will get the C2. The C4 is not here in this one, right? C5 is also not here. But here is the C6 there. We can rotate this one. I'll just finish it up. Right. Up to here we can rotate. So how many operations are like this possible? So C6 is there. C7, C8, C9 not there, right? So C6, the N is highest in principal axis. N should be the higher, right? So here it is C6 is the principal axis. How it is? It passes through like this. So this one is the principal axis, right? And the plane which is perpendicular to the principal axis, which is called as the sigma H. Let's say the plane, this molecule is in the plane, this plane, right? And axis is this perpendicular to this. So this plane is called as the sigma H. Uh, does it have the sigma V? The sigma V we need to take whether it has the sigma V or not. So this plane is called as sigma H plane. I will just rub all this. So if you pass a plane, right, which is perpendicular to the initial plane, right? How it pass through like this to this one, this one is in part. So it's having the sigma V plane as well. Sigma V means the plane parallel to principal axis. This is the sigma v plane. And see here also you can see, suppose this one is the principal axis and the plane which is parallel to the principal axis is called as the sigma v. And what is sigma d? The sigma d, which is the mirror plane which bisect the two C2 axis. This one is somewhat advanced example. So with the core progress, we can see this uh, sigma d also, example of some sigma d also, right? The plane which bisect the two C2s is called as the sigma d. Here we can take example of some system. So I'm able to suppose it's a platinum complex. Let's say here n n. Suppose take any atom a a a is attached, and principal axis will be, this one is the principal axis, right? And these are the, suppose take here will be the C2 also there, since it's a perfect square, right? We can pass C2 like this, C2. So after doing operation, this A atom will go this side, right? So it has the C2 also, right? So this is the principal axis, that is C4, and C2, how the C2 will go? C2 passes to this one. Here is also there is one C2, right? So this plane which bisect this two C2, here is C2 and the second C2 will be here, right? Here is the C2. By this direction, here is also one C2. So the plane which bisect the two C2 axes is called as the sigma D. There are some other example also. We can see this one in the upcoming video. So these are the some symmetry operations, right? So we have covered all the symmetry element, symmetry operation, and this what we call symmetry operation with some examples. And the point groups are also, there are different point groups. We'll see the point group in the upcoming next classes. In between, we'll solve some small problems on this one. So here is the one example. We need to just identify the correct statement of in this one. So first example, the first problem in this one. Consider the following molecule. Identify the correct statement. What are the four statements are shown here? The molecule has sigma and S1. Molecule has sigma and S2. Wait a minute. I'll just right. Uh, Here we need to consider this in this molecule. They said whether it has the sigma S1, which is correct statement we need to identify. Sigma S1, sigma S2, C2, and S4. Molecule has C2. So you need to verify all these things, right? So which is correct statement we need to identify. Here we can see this molecule. So hydrogen is there. Here is also hydrogen. It has the C2 axis. How we can check whether it has C2 or not? So let's pass the plane, plus pass a axis to the center and rotate it by the 180 degree. How this molecule will look like, right? So after 180 degree rotation, this hydrogen will go here. Similarly, this hydrogen will take this position of this previous hydrogen. Similarly, AS will be here, here, the AS will be here. The hydrogen at the bottom will go here, hydrogen at the AR will be here, AR will be here, and here will be another side. Right. So after the performing C2 operation, the molecule remain unchanged. So the molecule has the C2 axis. Also, we can take another possibility where the C2 was axis there. So this may be the correct statement, but we need to check here. There they have not mentioned it has the C2 or anything. So we need to check this S4 is also there or not. So how we can check check S4? What S4 means C4 plus sigma perpendicular, right? So we'll take the first C4 here, and then they will take the sigma. So once we do the C4 operation, how it will be the molecule look like? You can see here in this one, this same molecule. We have uh, rotate the molecule by 90 degree. So by rotating molecule by 90 degree in this direction, let's say the clockwise direction. So the AR group will become here, right? Previously it was here. After rotation, it will go the position of the hydrogen. And similarly, all other atoms will change the position, right? So this is the uh, S4 operation in which we have performed first C4. Then we need to take the sigma perpendicular. The sigma, since this axis we have passed like this, so we need to take the sigma which is perpendicular to this one. So we have taken sigma operation, sigma perpendicular to the axis. So the plane which is perpendicular to this molecule, we have passed a plane. So upper group will become lower, right? Downside. And here you can see this hydrogen. Previously it was downside, it will come upside. The AR group will be upside, so it will go downside. Why it go the downside? Since we have why it show the S? Since after taking a mirror plane, the configuration of the R changes to S configuration, right? So it will go, it will be printed as the S. And here also the molecule will change their positions. So we can see we can have a look here the previous uh, the final version and the initial one, how it exactly looks the same or identical. So it has the S4 also. So which statement is correct? So here the C1 is the correct, that molecule has the C4 as well as the S4. In the second one, given a flexible molecule is chiral if one of the conformation has improper element of symmetry. If option A. Another option is the none of the conformation has any improper element of symmetry. Third one is no. One of the conformation has simple axis of symmetry. And fourth option, none of the conformation is chiral. In this one, we can see molecule is flexible. Flexible molecule is a achiral if one of the conformation has improper element of symmetry. Then only molecule will be the achiral. Improper element of symmetry means we have seen proper element of symmetry and improper. Proper, what are the elements are there in the proper element symmetry? There will be the CN axis. That is axis of symmetry will be the proper element symmetry, and improper means sigma. Sigma in any kind of sigma, sigma V or either sigma D or sigma H. Any kind of sigma fall in the category of the sigma. Second one is the I, inversion center. If there is inversion center, then molecule obviously by default it will be the achiral molecule. But and if there is a SN, then also the molecule will be the achiral. So flexure molecule is achiral if one of the conformation has the improper element simply. Right. So this one is the correct option. Here some explanation also given. The presence of even one achiral conformation due to the presence of improper element of symmetry make the whole compound optically inactive. This thing we need to understand. Let's take some easy example. So you need to identify the point group of the following molecule. So this is the molecule, two molecules they have given, and we need to identify the point group. So here, what are the point group of this molecule? The point group in this one, we need to draw this conformation in a board form. Then only we can able to understand this one. So I'll just here the molecule I have drawn here. So in this you can see the first molecule. This one is the first molecule. So in this one, if we go opposite direction here, also opposite direction, we can found here it has the inversion center, right? Is there any CN axis or anything? No, there is no any CN axis, right? And another one, one we need to check what are the another one possibility. Any kind of rotation or reflection plane. If you take the reflection like this, no, it doesn't have any reflection, right? We need to check all these possible way. Inversion center is there only. Does other CN is there or not? No, no anything. So if you pass axis, no, we cannot pass. Like this also you are not able to pass the axis, right? So CN will be not there. Any kind of SN axis, SN axis also not there in this one. So this molecule belongs to the CI point group. In this one, if you see this molecule here, in this one, there will be no any kind of symmetry element present. But although there is no anyone, it will take a point and rotate the molecule by 360 degrees, right? Means which operation it is? Identity operation, right? So this molecule belongs to the C1 point group. Only identity operation is present, so this molecule belongs to the C1 point group, and this first molecule belongs to the CI point group. In this question, you can see, consider the three compounds. Let's say three compounds A, B, C given below, right? A, B, C, and D. Below are the conformation equilibrium. These conformations are in the equilibrium, okay, at ambient temperature, and the individual chirality of the conformation is given here. You can see here A compound is given in 1, 2, 3 different conformation. 1, 2, 3 different conformation is given. In first conformation is chiral, second conformation is achiral, third one is the achiral. We need to note that if any achiral possible, then the whole molecule or compound becomes achiral, right? So here, first one is the first conformation chiral. but second is achiral. So this molecule is not a chiral molecule. Since here is achiral one conformation present. In this one, for this B molecule, first conformation is chiral one, second conformation is also chiral one, third conformation is also chiral one. So this compound should be a chiral compound, and it's optically active. It should be the optically active compound, right? In so this one is the chiral compound. Second one, this one is the achiral. First one is the achiral. Second one is the chiral compound. C compound, you see achiral is there. First component, second component is achiral, third component is achiral. So all components are achiral, the molecule will become optically inactive, and it will be finally achiral. In the last D, in last D, first it has a one component, a chiral component. Second is achiral component. Third component is a achiral component. So this molecule is also optically inactive, and this will be the optically inactive compound, right? So identify the correct statement of the following. What here given in the first one, A, B, C, D, all are chiral compound. A, B, D are all chiral compound. Exactly wrong. This is obviously a wrong. Since it has the here a chiral conformation. In the C also here is one a chiral conformation. Here also one a chiral conformation. And A here is a chiral conformation. Since whenever any possible conformation which is a chiral one, the whole molecule or compound become a chiral or optically inactive. This thing we need to keep in mind. Second, what option they have given? A has more chiral conformation than D, so the specific rotation of A should be greater. No, there is no any such relation with the optical rotation and the conformation. A, C, D, all are achiral compound. What they have given? A, C, D. This one A, C, D, all are achiral. Right, exactly. This will be the correction. This is the correction. And what last statement they have given? Only C is a chiral compound. In the C, achiral, C is achiral. But see, you can see here achiral they have given. Here is also achiral. This is wrong compound. Only C is achiral compound. No, it's a wrong statement. So the correct answer is the C. This one is the correct answer. A, C, D, all are achiral compound. So we need to always keep in mind, if uh, please note this point, if any achiral conformation is possible for a molecule, then whole compound should be become optically inactive or achiral compound, right? So this was the some problems. Remaining problem we will see in the next lecture. Thank you so much for joining. Please, if you have any query, please let me know. Uh, I will just stop recording. So in between, you just check the today's notes and just tell me any doubt you have.